People ask me all the time, Professor, what is time? And I always say the same thing, sit down because you're not going to like the answer. Here's the thing. Right now, watching this, your clock, my clock, they are not ticking together, not sort of, not close enough, literally different. And neither of us can feel it happening. Is that a strange thing to sit with? Now, most people walk around assuming time is like one giant drum beat, playing the same rhythm for the whole universe. Tick, tick, tick. Same for you, me, a guy on the moon, a rock floating near a black hole. 1 second here, 1 second there, universal, right? Wrong. And I mean delightfully wrong. Time isn't a drumbeat at all, it's personal. It stretches, it bends, it slows down or speeds up depending on how fast you're moving and how much gravity's pulling on you. There's no master clock sitting somewhere in the sky keeping everybody honest. Think of it like this. Two friends leave a party. One drives home on the highway, the other walks. Nobody's confused when they don't arrive at the same time. Of course they don't. They travel different paths. But somehow we never think time works the exact same way. Your journey through space changes your journey through time. Nobody tells you that in school. And this isn't some armchair philosophy. I can prove it to you. We've got atomic clocks so precise they'd lose 1 second every 300 million years. Put one on an airplane, leave one on the ground. They disagree when the plane lands. NASA's measured it. And here's the kicker, your phone's GPS has to correct for this every single day or your map would send you into a lake. That little device in your pocket only works because engineers had to admit time moves faster up there than it does down here. Now, if a satellite orbiting Earth can throw time out of sync, what do you think happens when something moves impossibly fast? Say, the speed of light itself? Now, here's something that'll keep you up at night. There's exactly one thing in this whole universe that nobody, not you, not me, not even Einstein himself, could ever catch up to. Not with a faster rocket, not with a cleverer trick. Once you understand why, I promise you the world looks different. Most people hear speed of light and think, well, that's just a really fast bullet. Faster car, faster bullet. Faster light, it's all just degrees on the same scale, right? No, and this is where it gets fun. Light isn't just fast, it's the speed limit of reality itself, 299,792 kilometers a second. And here's the part that breaks people's brains. That number never changes. Doesn't matter who's measuring it, doesn't matter how fast they're moving. Everybody gets the same answer. Always, let me give you a picture. Say you're on a train doing 100 kilometers an hour and you throw a ball forward at 20. Somebody standing on the platform watching you go by, they measure that ball at 120. Simple addition. Makes sense. Everybody's happy. Now swap the ball for a flashlight. Turn it on. That person on the platform, they measure the light going at exactly the same speed as if your train had never moved at all. Light just refuses to add up the normal way. It breaks the rule every single other thing in the universe obeys. This drove physicists absolutely crazy back in the 1880s. They couldn't make sense of it. Took a young patent clerk named Einstein in 1905 to say, maybe the speed isn't wrong. Maybe our idea of time is wrong. I've always said this is one of the strangest, most beautiful things nature ever pulled on us. So think about it this way. If speed refuses to bend, refuses to budge, ever, something else has got to give. Something has to bend to keep the whole universe making sense. And that something, that's time. Here's one that I love because it sounds like a trick and it's not, it's just nature being clever. What if I told you that the faster you move through space, the slower you move through time? And you're doing this right now, sitting there, not moving an inch. Still true. Now, the normal way to think about speed is speed gets you places faster. That's the whole point, right? Drive faster, arrive sooner. Nothing about time changes, just your arrival. But that's not quite the full picture. See, space and time, they're not two separate things happening independently. They're stitched together into one fabric, what we call space-time. And here's the beautiful part. Everything in this universe is moving through that fabric at one fixed total speed. You don't get to change how much you're moving, only where that motion goes. Picture driving a car that's stuck at exactly 100 kilometers an hour, no more, no less. But you can steer that speed between forward and sideways. Steer more sideways, and you've got less left over for forward. That's exactly what's happening between space and time. Speed up through space, and you're borrowing from your motion through time. There's only so much to go around. Now, here's the part that gets people, even sitting perfectly still, doing absolutely nothing. You are moving through time at the maximum possible rate, the fastest anything can experience. Einstein worked this out mathematically. I like to picture it with a simple light clock. Just a beam of light bouncing between two mirrors, ticking away. Get that clock moving, and geometry alone forces it to tick slower. No trick, no magic, just triangles. So here's your mind bender for the day. You are, quite literally, always traveling at the speed of light, just not always through space. Sometimes almost all of that speed is spent moving through time instead, which begs the question, if speeding up through space steals from your time, what happens when you push that speed all the way to the edge? What happens when there's no time budget left to spend at all? All right, picture this with me, an astronaut, zooming through space at 99.9% the speed of light. Now, to her, sitting in that cockpit, everything's normal. Her coffee's cooling at the regular rate, her heart's beating right on schedule, her thoughts are ticking along just fine. But to you, watching from back here on Earth, she has almost completely stopped moving through time. Now sit with that for a second. Most people, when they imagine going that fast, they picture something dramatic. Maybe you'd feel yourself speeding up, or your clock would spin wildly, something you could notice. But no, that's not how it works at all. Inside that ship, nothing, and I mean nothing, feels different. That's the sneaky part. Here's a picture I like. You know that awful video call, the one with the terrible lag? The person on the other end thinks they're talking at completely normal speed. From their side, everything's fine. But to you watching, they're crawling along in slow motion. That's relativity in a nutshell. Each person thinks their own clock is ticking just fine. It's only when you compare the two that the weirdness shows up. And listen, this isn't some thought experiment I'm just making up to sound clever. Over at CERN, they're slinging particles around in that giant tunnel at 99.9999991% the speed of light every single day. And these particles have their own little internal clocks, how fast they decay. And sure enough, those clocks run slower, exactly matching what Einstein predicted, down to the decimal. NASA deals with this too, tracking spacecraft, correcting for it constantly. Now here's the kicker. The closer you creep toward light speed, the more extreme this gets. Not gradually either. It accelerates dramatically near the end, until, from an outsider's view, time for that traveler practically grinds to a halt. So now I've got to ask you the question that's been eating at physicists for over a century. What happens if something didn't just get close to light speed, but actually reached it? Does time just slow down a whole lot more? Or does it stop completely? Now here's one that still gives me a chill, and I've thought about it for years. For a photon of light, zero time passes between the moment it's born and the moment it dies. None. Zero. Even if that journey takes it 13 billion years to reach us, streaking across the entire universe. To the light itself, no time at all. Now, most people, when they imagine traveling at light speed, they think, okay, it'd be slow motion, but extreme slow motion, like everything crawling by, but still happening, still some kind of experience going on in there. But no, that's not it at all. At light speed, time doesn't slow down to very slow. It stops completely, dead stop. A photon leaving some distant star tonight, traveling for billions of years before it lands on your eyeball. From that photon's perspective, there was no in-between. None whatsoever. Here, let me paint you a picture. Imagine watching a movie in slow motion, one frame every few years, painfully slow. Now keep slowing it down and down until the film simply never advances past a single frame. Ever. That's not slow anymore. That's frozen. Locked. One eternal instant. That's what light experiences. This is why we say light doesn't have a journey at all. It doesn't experience the trip between leaving and arriving. I used to draw these things out on space-time diagrams, little maps of space and time together, and if you trace out light's own path on one of those, its birth and its death sit at the exact same point, simultaneous, no matter how far it traveled by our clocks. Think about that for a second. Every single photon that has ever existed since the universe first lit up has experienced exactly zero time. To light, the entire 13 billion year history of the cosmos isn't a story unfolding. It's one single, frozen moment. Now, that raises a question that should make you a little uneasy. If light experiences absolutely nothing, how in the world did Einstein and later people like me ever manage to imagine something so completely outside of human experience? You know, I once said if you think you understand quantum mechanics, you don't understand quantum mechanics. I'll stand by that. But time, light, relativity, that stuff, that I could actually make click. Let me show you how. Now, people assume this relativity business needs a chalkboard full of equations and a degree from somewhere fancy to even approach. Nonsense. If you can't explain something simply, you probably don't understand it yourself. That was always my rule. So here's how I like to picture it. Imagine a light clock, just two mirrors facing each other with a single beam of light bouncing back and forth between them. Every bounce, tick. Every bounce, tick. That's your clock. Now put that clock on a moving spaceship and watch it from outside. From your view, the light isn't just bouncing straight up and down anymore. It's got to travel diagonally because the whole clock is sliding sideways while the light bounces. And diagonal is longer than straight up and down. Longer path, same speed of light means each tick takes longer. The clock runs slow. That's it. No mystery, no magic, just triangles. Here, try this one. Bounce a ball straight up and down standing still. Quick little bounces, right? Now bounce that same ball while riding in a moving car. Someone watching from the sidewalk sees the ball trace a longer zigzaggy path. Takes longer to complete each bounce, even though nothing about the ball itself changed one bit. Same exact idea. I always believed the deepest truths in physics should be explainable to a curious kid. That's basically been my whole career. Manhattan Project, quantum electrodynamics, all those lectures at Caltech. Didn't matter how complicated the topic was, I always hunted for the simple picture hiding underneath. And here's what falls right out of this light clock business. Time dilation isn't some weird arbitrary rule somebody made up. It's a direct, unavoidable consequence of one single fact. Light speed never changes. Everything else, all the slowing, all the stretching, just falls out of that, like dominoes. Now, this all sounds lovely as an idea, but has anybody actually gone out and measured real clocks disagreeing with each other? Oh, you're going to want to hear this one. Now, here's my favorite kind of story, one where somebody actually went out and tested the crazy idea instead of just arguing about it over coffee. Back in 1971, a couple of scientists, Haffele and Keating, took atomic clocks, put them on commercial airplanes, and flew them clean around the world, just to see if time itself would come back different. And you know what? It did. A lot of people hear time dilation and figure, that's just chalkboard stuff. Pretty equations that never actually touch the real world. But no, this thing has been tested over and over with just ridiculous precision, and every single time it checks out exactly the way Einstein said it would. Here's a picture worth holding on to. Identical twins. One stays home on Earth. The other blasts off in a rocket, zips through space at tremendous speed, and comes back. When that traveling twin steps off the ship, they are measurably younger, not feels younger. Actually younger, provable on paper in years and days. We call this the twin paradox. And it's not science fiction, it's been backed up by real experiments. Speaking of which, that 1971 experiment I mentioned. The flying clocks came back disagreeing with the ground clocks, exactly matching the prediction. And get this, astronaut Scott Kelly spent nearly a year up on the International Space Station, and when he came home, he was about 5 milliseconds younger than his identical twin brother Mark, who stayed right here on Earth. 5 milliseconds! Tiny, but real, measured, undeniable. And here's the one that gets me every time. GPS satellites experience time almost 38 microseconds faster every single day compared to us down here, just from their speed and altitude. If engineers didn't correct for that constantly, your GPS would be wrong by miles within hours. Global navigation would just fall apart. So think about that. Every time you glance at your phone for directions, you're relying on a working correction for the fact that time runs differently up in orbit. This isn't tucked away in some laboratory. It's active, in your pocket, right now. So we've proven the traveler's time really does shift. But here's what I want to know next. What does that traveler actually see while it's happening? And even better, what would you see watching from right where you're standing? Here's a good one. If you flew a spaceship near the speed of light for what felt like just 5 years to you, you could come back to Earth and find your grandchildren old and gray, or gone entirely. Sit with that a moment. Now, most people, when they picture this, imagine the traveler noticing something, like they'd feel themselves slipping into slow motion, watching their own hand move like molasses, like a scene out of a movie, but that's exactly backwards. The traveler feels nothing unusual, not one thing. Time always feels perfectly normal to whoever's experiencing it. Doesn't matter if you're standing still or screaming through space at 99% light speed. Your coffee tastes the same. Your thoughts flow the same. It's only when you stop and compare your clock to somebody else's, somebody in a different reference frame, that the difference jumps out at you. Here's a picture I like. Two friends on a video call. One's riding a fast-moving train, one's sitting still at home. During the call, both of them feel like the conversation is happening in perfectly normal real time, nothing odd at all. But later, if they pull up the recordings and lay them side by side, one video's stretched out compared to the other. Neither friend felt it happening in the moment. The weirdness only shows up when you place the two realities next to each other. This is exactly why relativity gets called counterintuitive but consistent. Everybody feels normal, and yet everybody disagrees. I always like to remind people, nature doesn't owe you common sense. It doesn't care what feels right to a brain that evolved to chase gazelles across a savanna. It just is what it is. Now here's the part that ought to give you goosebumps. If we ever build ships that travel near light speed, an astronaut could head out for what feels like a 5-year mission and come home to find decades, maybe centuries, have passed on Earth, their friends gone, their world unrecognizable. A 5-year trip that was secretly a one-way ticket into humanity's future. So if near light speed travel can fling you forward in time like that, what happens near the strangest, most extreme objects in the entire universe? Black holes. What does that do to the fabric of reality itself? Here's one to keep you up tonight. Somewhere out there right now, near the edge of a black hole, time is ticking so slowly that a single hour could equal decades back here on Earth. 1 hour, decades. Let that rattle around in your head for a second. Now, most people hear all this talk of time bending and figure, that's just for astronauts. Rocket ships, futuristic speeds, nothing that touches real cosmic events. But that's only half the story. Speed isn't the only thing that messes with time. Gravity does it too. And when you combine the two, speed and gravity, out in the most extreme corners of the universe, you get scenarios so wild they sound like they were invented for a movie, except they weren't invented. They're just how nature works. Here's a picture. Think of an escalator that slows down the closer you get to the bottom. That's gravity near a black hole. The closer you creep toward it, the slower time moves for you compared to somebody watching safely from far away. Hover just outside that black hole for what feels like a few minutes to you, and years, maybe centuries, pass for the rest of the universe. This isn't some story I'm spinning for fun either. That gravitational time dilation showed up famously in Interstellar, and physicist Kip Thorne made sure the physics behind it was real, not just movie magic. When those scientists captured the first ever image of a black hole back in 2019, they were leaning directly on Einstein's equations to make sense of what they were seeing. And even our everyday satellites, the ones running your GPS, have to correct for gravity's effect on time, or your map would drift off within hours. So here's the real kicker. If humanity ever builds a ship that can travel a meaningful fraction of light speed, interstellar travel stops being just exploration. It becomes literal time travel, forward, one direction only. No return ticket to the world you left behind. So now think about everything we've covered. Light freezes time completely. Speed bends it. Gravity warps it. After all that, what does it actually tell us about what time really is? So let me leave you with the big one. The thought I want rattling around in your head long after this video ends. Time is not something the universe has. Time is something the universe does. And you have been walking around your whole life inside an illusion without ever realizing it. Most people picture time like a river, one river flowing at one speed, carrying all of us downstream together, past, present, future, marching along in lockstep for everyone everywhere. Feels obvious, doesn't it? Except it isn't true. There is no universal now, not one. Every single observer, you, me, somebody on a spaceship, somebody near a black hole, each moving at your own speed in your little corner of the universe, you're all experiencing your own personal timeline. And here's the part that'll really get you. All of them are equally real. Not approximations of some true time, actually genuinely real. Einstein himself, late in his life, wrote to comfort a grieving family by saying the separation between past, present, and future is only a stubbornly persistent illusion. A physicist saying that about time itself. Here's a picture worth keeping. Imagine millions of people wandering through the same museum, but every single one walks a different pace, takes a different path. They're all in the same museum, technically, but never experiencing it in the same order, never at the same moment, never from the same angle. That's the universe. And time? Time is simply the path you take through it. I spent my whole career trying to show people that underneath all this strangeness, relativity, quantum mechanics, all of it, there's a universe far stranger and far more elegant than anybody could have dreamed up without letting the evidence do the talking. So here's your final twist. You're not just moving through time. You are time in a sense, shaped by your speed, your location, woven into that invisible fabric connecting space and time together. And somewhere, right now, another now is unfolding at a completely different pace than yours. Just as real, just as valid. Forever. So next time you glance at a clock, remember, you're not watching time pass. You're watching your version of reality unfold, one nobody else in this entire universe will ever experience in quite the same way.